Okay, let's continue with section 4.1. We had just finished doing some sketching of angles in radian measure to get a good feeling for what radians were like. And the next problem is converting between radian measure and degree measure. So remember we proved in the last video that pi radians was equal to 180 degrees. So halfway around in degrees was 180 degrees, halfway around in radians was pi radians. Okay, so we already talked about doing dimensional analysis, unit conversion earlier, so we don't have to explain that whole process. We know how to do it. So the first problem says, well, it says convert from degrees to radians or vice versa. Give exact answers. Remember, exact answers means do not punch in the calculator and round. Okay, that is not exact, means leave the pi alone, leave square root of 3, leave square root of 3 alone instead of punching in and rounding. Okay, so the first angle they give is 2 pi over 3. Now the question is this in degree measure or is this in radian measure? Okay, now hopefully you said radian measure. Now the important question is, how do you know this is in radian measure? Now if you said because there's a pi in the problem, that's not the reason, right? There's no degree sign. Remember, when there's a degree sign, that means degrees. If there's no units listed, that means radians. You can have an angle of pi degrees. Just because there's a pi in the problem does not mean it's radians, right? It's the degree sign, or lack of, that tells you what measure. So 2 pi over 3 is in radians because there's no degree sign. Okay? Now I'm going to go ahead and think of this as a fraction with radians in the numerator. Okay? Because I'm going to use my, change of units thing. Okay? So I want to go from radians to degrees. So if radians is in the numerator, I want to get rid of it, cancel it by having it in the denominator, which means I want degrees in the numerator. Okay, so the radians will cancel and I'll have degrees left. Now, how many degrees is how many radians? 180 degrees is pi radians. Okay, that's just the fact you have to remember. Just like 3 feet is in a yard, or 60 seconds is in a minute, 60 minutes is in a degree. Notice the radians units cancel, the pi's cancel. So if you do 2 times 180 over 3, you're going to get 120 degrees. Now don't forget your degree signs. The whole point of this problem is converting units, so it's important to have your degree units here when you mean them. Okay, let's do the next problem. Now this is clearly in degrees. Think of that as over 1. So now let's do units first. Don't worry about the numbers. I have degrees here in the numerator. I want to get rid of them so they go in the denominator, which means I want radians here. Again, you don't have to write radians. I like to put them in here because we're doing unit conversion. And then how many radians or how many degrees? Pi radians is 180 degrees. So the degrees units cancel. I'm not going to simplify yet. So I get negative 270 pi over 180. And I don't have to write radians now because, I'm done with the unit conversion. I know that's radians because I didn't write a degree sign. And normally, I will expect you to simplify fractions. 90 goes into 270 and 180. 90 goes into 273 times, and 90 goes into 180 2 times. You should always simplify your fractions. I can be forgiving if it's not an obvious simplification, but it's clear 90 goes into both of those. Okay, so that's that one. Right? Try this last one on your own. Pause the video and do the conversion of 315 degrees to radians. So pause the video and do it yourself, and then start it again, and then I will do it. Okay, now that you've done the problem, think of 315 degrees is over 1. Okay, so this is degrees. I'm going to radians, so I want degrees in the denominator and radians in the numerator. And pi radians is 180 degrees. So the degrees cancel, and I get 315 pi over 180. Again, you should simplify your fraction. Let me see. I think 45 goes into 315 and into 180. 45 goes into 184 times. And 45 goes into 315, 7. So you get 7 pi over 4. Okay, so that's that one. Again, if you want to write radians, that's fine. If you don't, that still means radians. Okay, so that's how we do conversion. Now, I listed some of these common ones in the notes. So 30 degrees is pi over 6 radians, 60 degrees is pi over 3 radians. That's easy to remember. If you do the procedure we just did on 30 degrees and 60 degrees and 45 degrees and 90 degrees, this is what you would get. But you may just want to memorize it. So notice there's a 3 and a 6 in both of those. 60 degrees is pi over 3, 30 degrees is pi over 6. There's a 6 and a 3. 45 degrees is pi over 4, and 90 degrees pi over 2. It makes sense, right? Pi radians was 180 degrees. Half of 180 is 90, so half of pi would be the pi over 2. And then notice half of 90 is 45, so half of pi over 2 is going to give you the pi over 4. But again, you may just want to memorize those. There's no need to, you don't want to convert these over and over and over again because they show up all the time. Okay, so now we're going to shift gears again. Again, there's many, many topics in this section 4.1. So each one's not that hard, but it's just difficult because there's so many topics. We're doing all the geometry in one section. Okay, the next definition says if the sum of two positive angles is pi over 2 or 90 degrees in degree measure, we say the angles are complementary. Notice complementary is spelled C-O-N-P-L-E. Complementary with an I, C-O-M-P-L-I, is paying someone a compliment. You know, how nice you look today. That's a compliment with an I. Or you get a complimentary drink when you buy a buffet, buy a dinner entree. That's C-O-M-P-L-I. So, if the sum is pi in radian measure or 180 in degree measure, the angles are called supplementary. I used to get them confused. Which one's complementary, which one's supplementary. If you do degree measure, complementary is they sum to 90 degrees, supplementary is the angle sum to 180. They're think alphabetical. Complement or supplement 90 before 180. And in radian measure, that's pi over 2 and pi. Obviously, 90 degrees is pi over 2 radians, 180 degrees is pi radians. So that may help you remember. Okay, so the next example is practicing with this. It says find the complement and supplement of each angle. If the angle is given in degrees, give the answer in degrees. If the angle is given in radians, give the answer in radians. That's going to be true throughout the rest of the course. If you're given information in degrees, everything else, if you have another angle in the problem, give it in degrees. If the angle is given in radians, you should get everything in radians. Okay, so the first one says 20 degrees, and we want the complement. You should label your answers when you're doing work and supplement. Okay? Well, how do we get the complement? Right? Two angles are complements of one another if they sum to 90 degrees. Well, if one of them is 20, how do you get the complement? It'd be 90 degrees minus 20, which is 70 degrees, right? 70 plus 20 is 90. Well, how do you get the supplement? Well, two angles are supplements of one another if they sum to 180. So 180 minus 20 would be 160. Right? So these two add up to 90. They're complements of one another. These two angles add up to 180. They're supplements of one another. Okay, the next example says do the same thing or pi over 7. Now that's radians. So we want the complement and we want the supplement. Now here you have to think in terms of radians. Two angles are complements of one another if they sum to pi over 2. Okay? Now, how do we get the answer 70 here? If you know one of the angles is 20 degrees, and the complement will add, is what's left when you add the 90, was 90 minus 20. And the supplement was 180 minus 20. It's the same computation in radians. Right? Pi over 7 plus what is going to give you pi over 2. So I need pi over 2 minus pi over 7. It's the exact same computation we did here, except for we're in radians. Now we have to do some arithmetic here. We need a common denominator. The least common multiple of 2 and 7 is 14. So I need to multiply the first fraction by 7 over 7 to get the 14. I'm multiplying by 1, so I'm not changing the value, I'm just changing the appearance. And the second fraction, to get to 14 in the denominator, I need to multiply by 2 over 2. Again, I'm multiplying by 1, so I'm not changing the value, I'm just changing the appearance. So notice this is 7 pi over 14 minus 2 pi over 14. To multiply fractions, you just multiply cross, and you get 5 pi over 14. Yes, you should be able to do this calculation. Right? You learned how to do fractions in elementary school. Now, I know they didn't have pi's in them, but the idea is the same. Now, how do we do the supplement? Well, two positive angles are supplements of one another in radian measure if they sum to pi radians. So one of the angles is pi over 7. The other one's going to be pi minus pi over 7. Same idea. We need a common denominator. Think of the pi as over 1. The least common multiple, least common denominator is 7. So I need to multiply, I need a 7 in the denominator, so I need to multiply the first fraction by 7 over 7. I'm multiplying by 1, so I'm not changing the value, just the appearance. And the second fraction you don't have to do anything with because it already has a 7 in the denominator. Right, so 7 pi, we have a 7 in the denominator, so to subtract fractions, when you have a common denominator, leave the denominator alone. 7 pi minus pi is 6. Okay, so that's that. And then the last example of this type, the angle is now 3 pi over 8. And we want the complement, and we want the supplement. Okay, now it's going to involve fractions like the previous example. Pause the video, see if you can do those complement, supplement of 3 pi over 8, and then run the video again, and then I will work it out. We'll see if we get the same thing. Okay, so for the complement of 3 pi over 8, right, two angles are complementary in radian measure if they sum to pi over 2. So if one of them 3 pi over 8, the other one is pi over 2 minus 3 pi over 8. We need a common denominator. The least common multiple of 2 and 8 is 8, which is nice. Notice on this one we had to change both fractions to the 14. This one already has an 8, so we don't have to do anything with it. So pi over 2 times 4 over 4, multiplied by 1. So I'm changing the I'm not changing the value, I'm just changing the appearance. Minus 3 pi over 8. So that's 4 pi over 8 minus 3 pi over 8 is pi over 8. Okay, now for the supplement, it's pi minus 3 pi over 8. The least, think of the pi's over 1, so the least common denominator is 8. Multiply the first fraction by 8 over 8. And the second fraction you don't have to do anything with because it already has an 8. And then 8 pi over 8 minus 3 pi over 8 is 5 pi over 8. So hopefully you've got those two answers. Okay, if not, look carefully at what I did and see what you did wrong. Okay, you have to be able to do fractions. Okay, the definition of bond, we're shifting topics again. So we just did complement and supplement. So the next topic is coterminal angles. Now why the phrase coterminal? We already talked about something about terminal when we did angles. Remember we had an initial side and that rotated to a terminal side. Coterminal is also referring to the coterminal side. So angles with the same terminal side are called coterminal. All right, now let's think about what that's saying. So again, we're talking about standard position. So the initial side's here. So suppose I had an angle with the terminal side here. And then I had another angle with the initial side here and the terminal side here. Well, if the initial side's the same for both, because we're in standard position, and the terminal side is the same for both, what's the difference? What could be the difference between the two angles if the initial sides are both here and the terminal sides are both here? Remember, there's another part to an angle besides the sides. It's the rotation. Okay, so one angle could do this, and another one could do this. So those would be coterminal angles. They have the same initial side, same terminal side, but they're not the same angle because the rotations are different. Okay, if the rotation's the same, it's the same angle. Now let's think about this for a second. Suppose I had this angle right here, right, and I wanted to find an angle that was coterminal with this. So it started here and stopped here. Well, if I went from here to here, that's the same angle. What if I wanted a completely different angle? What could you do? Couldn't you go all the way around and stop there again? That would be coterminal because they both started here and stopped here. What if I wanted another one? Right? So once I'm here, we'll go around again and stop there. That would be another coterminal angle. Or what if I was here, okay, same picture, couldn't I come to here and then go backwards all the way around? So what's the net result? If I go from here to here and then backtrack, I basically, cancel those out. So I've really started here and stopped here. But what's the net result? I mean, you're going to have an angle that stops at the same place the original one did. So if you have an angle and you want to find angles that are coterminal with it, what do? Wherever you are, add a rotation or subtract a rotation, and you're going to be back at the same place. Like the terminal side will be at the same place. That's all you have. That's all I was explaining was how do you figure it out without drawing the picture? Okay? So wherever the angle ends up, wherever the terminal side is, how do you get another angle coterminal with it? Add a rotation or subtract a rotation. And if you want another one, you could add or subtract another rotation. So that's what the next two examples are about. They give you this angle 90 degrees, and they say find two positive angles and two negative angles that are coterminal with 90 degrees. Well, I don't need a picture here based upon what I just explained to you, but let's do a picture of 90 degrees. There's 90 degrees. If I wanted another angle coterminal with it, what could you do? Right? There's 90, go all the way around and stop there again. That would be an angle that's coterminal. So what do you have to do? Just add 360 to this. So another one would be 90 plus 360, which is a 450. So 90 degrees and 450 degrees are coterminal. So 90 is just from here to here, 450 is to here, and then all the way around. Well, how could you get another one? Well, 450 is coterminal with 90. If I add a 360 to that, I get, what, 810 degrees. So 90 and 450 and 810 degrees are all coterminal. Now it also said to find two negative angles that are coterminal with 90 degrees. Well, if you're at 90 degrees and you want to get a negative angle coterminal, subtract 360 from it. 90 minus, that's negative 270 degrees. Now think about what that is. So 90 degrees is here, negative 270 is here. Because what have we done? You went up to 90 and then subtracted 360. So again, those dropped out. You just went from here to here. There's your negative 270. Now I said to find another one, so negative 270 minus 360 degrees is what, negative 630 degrees? You can always check my arithmetic. Okay, so there's two positive angles coterminal to 90 and two negative angles coterminal to 90 degrees. Okay, now it says do the same problem with negative pi over 4 radians. Okay, so it's a negative angle here. So I'm at negative pi over 4. Now what do we have to add to that to go all the way around? Remember, 2 pi radians was one complete revolution. So instead of adding 360 degrees, we're going to add 2 pi. Now again, we're going to have the fraction issue. Think of the 2 pi as over 1. Least common multiple of 1 and 4 is 4. So we have negative pi over 4. And I need to multiply this fraction, 2 pi over 1 times 4 over 4. Again, I'm multiplying by 1, so I'm not changing the value, just the appearance. And so I get negative pi over 4 plus 8, plus 8 pi over 4, which is 7 pi over 4. So there's a positive angle coterminal with minus pi over 4. So what this one is, right, here's the minus pi over 4 here, and 7 pi over 4 is this one, right? So they stop at the same place. Okay, now that's only one positive angle, so now we have a 7 pi over 4, and we need to add the 2 pi to that. Right, so we went to 7 pi over 4, now we have to go all the way around again, so we're adding another complete rotation. Again, think of that as over 1, 7 pi over 4 plus the 8 pi over 4 again, right, that's 2 pi. 15 pi over 4. So minus pi over 4, 7 pi over 4, and 15 pi over 4 are all coterminal. But it also said to find two negative angles, so now I'm starting with the minus pi over 4, and I want to subtract 2 pi from it. Right, so minus pi over 4, the 2 pi over 4 became the 8 pi over 4, so it's minus 8 pi over 4, which is minus 9 pi over 4. So there's a negative angle coterminal with minus pi over 4, and now we're at minus 9 pi over 4, and we want to subtract another 2 pi from that. So it's the same calculation, minus 8 pi over 4, there's your 2 pi, and that's minus 17 pi over 4. So minus pi over 4, 7 pi over 4, 15 pi over 4, negative 9 pi over 4, negative 17 pi over 4, those are all coterminal. They're not the same angle because the rotation's different, but the initial side is positive x-axis, the terminal side is down here in the fourth quadrant. So all four of those start there and stop there, but they have different rotations. So there's coterminal. Okay, now there's two last ideas in this section. And the first is arc length. So I want to explain where the formula is coming from. Since you are science majors, you need to understand where these formulas come from. Okay, so the first one is arc length. So I left room to draw this picture. We don't really need that much room, but Okay, so here's a circle. Okay? So let's imagine a central angle here. Remember, a central angle is an angle whose vertex is at the center of a circle. And I'm just going to draw something. It doesn't matter. Okay, so and I'm going to call that angle theta. I'm not worried about the rotation there. Right? So this is the angle theta, the central angle. Okay. And the radius of the circle here we're going to call r. And the length of the arc intercepted by the central angle we're going to call s. I'm not sure why s is what they use, but that's standard. They use s. I've seen it lots of times. So we want a formula to express s in terms of r's and thetas. Okay, now I'm going to assume here theta is in radians. Okay, we're going to derive the formula assuming theta is in radians. We can do it in degrees, but the formula is more complicated. Okay, so does it seem reasonable? And the answer is yes. That if I took this angle in radians, the theta, divided by the angle all the way around, that would give me a fraction. That would be the same fraction as if I took the length of s divided by the length all the way around. Let me say that again. So I'm going to take the value of theta in radians divided by the angle all the way around in radians. That would be the same percentage as the length of s divided by the length all the way around. Those are going to be the same fractions. Okay, so let's set that up. So theta, that angle, divided by the angle all the way around. Now, theta's in radians, so the angle all the way around needs to be in radians. And what's the angle all the way around? That was 2 pi. Remember, 2 pi radians was all the way around. So I have radians over radians. The radians units cancel. This is just a fraction. It's just a number. There are no units on that. Right? Equals, okay? Now, I'm taking the length of s divided by the length all the way around. Well, that's the circumference of the circle. We talked about that earlier, right? The circumference of a circle is 2 pi r. Okay? So that fraction should equal that fraction, right? Theta divided by the angle all the way around is the arc length of s divided by the arc length all the way around. Now, if you cross multiply, if you have two fractions equal to one another, their cross product's the same. So I have well, let me do it this way. Yeah. So I have 2 pi s is 2 pi r theta. Right? 2 pi s is 2 pi r theta. But notice I have a 2 pi on both sides. They cancel out. I get s is r theta. Nice, easy formula, right? So the arc length is just the radius times the theta. Notice if theta is 1 radian, right? If theta is 1 radian, s is r. We already knew that, right? When we have 1 radian here, the arc length is the same as the radius. So we already knew that. Okay? Now, this is assuming theta is in radians. Okay? So how do you use this formula? If you plug in for theta in this formula to find something, theta must be in radians. If this formula spits out a theta, theta is in radians. It doesn't matter what the problem gives you or asks for. If you plug in for theta, theta has to be in radians. If it spits out theta, theta is in radians. Okay? And then you may have to adjust, if the problem asks for something else. So as an example here, okay, so s is r theta. Let me just write that underneath here and I'll give myself the more room. So this is for arc length. The length of the arc intercepted by the central angle theta. Okay? So there's a picture here. So there's a pulley. Okay? And there's a rope attached to the pulley with some weight hanging down from it. There's my interesting picture. It says the pulley has a radius of 9.3 inches. Okay, so that's the radius, 9.3 inches. Okay, so there's my rough picture. How many inches will the weight in the figure rise if the pulley has a radius of 9.3 inches and is rotated through an angle of 71 degrees 50 minutes, okay? So we're going to rotate, so imagine there's a handle here, and we're going to rotate the pulley up. And the angle we rotate through is 71 degrees 50 minutes. I didn't make it big enough to put the angle. The angle's here, right? That's the angle, 71 degrees 50 minutes. Okay, now think about what's the physical situation here. So the rope is attached here, it's solid, and we're going to rotate the pulley through an angle of 71 degrees 50 minutes. Now what's going to happen to this rope, right? As you rotate, the rope is going to wrap around. It's not going to go straight up in the air, right? It's going to wrap around the pulley because it's attached right here. So as this moves through that, the weight is going to come up. So notice the distance that the weight's going to come up is the same as the amount of rope that gets wrapped around. But notice the amount of rope that gets wrapped around is that arc length. Notice nowhere in the problem does it say find the arc length. It's an arc length problem, but it never says arc length. So you have to understand the physical situation here. Okay, so we're looking for this S. Okay, well, the formula's S is R theta. We're looking for S. We know R, and they gave us the theta. So S is just 7150 times 9.3. No. You have to be careful. Remember, I said when you plug in theta into this formula, theta must be in radians. They gave us degrees in minutes. Okay, so we have to do some conversion. Once we do the conversion, the problem will be very easy. That is the most common mistake I see on a problem like this, on, say, an exam or a quiz. Students will just do R times theta and tell me what the S is. Theta has to, when you plug in theta into the arc length formula, theta has to be in radians. Now, when we did conversion earlier, what did we convert from? Right? We converted from degrees to radians and radians to degrees. This is degrees in minutes. So what do we really need to do first? First, we need to write the 71 degrees 50 minutes in terms of decimal degrees, and then go from the degrees to the radians. Okay. Now we talked about how to do this earlier, right? 71 degrees 50 minutes, right? If this is 71 plus 50 over 60, so I'm just going to punch that in. So 71 plus 50 over 60 is, this is 71.83. I'm going to write a lot of digits here. 8333 degrees. Okay, remember we talked about this earlier, right? When you have degrees in minutes, how do you convert to decimal degrees? It's 71 plus 50 over 60 plus, if we had seconds, the seconds over 3600. Okay, so that's the quick way to do that. Now we have 71.8333 degrees. I want to convert that to radians, which we already know how to do. So degrees goes in the denominator, radians in the numerator, because I want degrees to cancel. And pi radians is 180 degrees. Now when we did these before, I left the pi alone and I simplified the fraction. We've already rounded here, okay? And we want to get a value for S, so we're not going to have a pi there. So go ahead and include the pi when you punch this in. Again, you should punch along with me. 71.8333 times pi divided by 180. This is about I'm going to write several decimals, 2537 radians. So I included the pi. I punched the pi in when I did that. Okay, so that's this 71 degrees 50 minutes in terms of radians. Now I'm ready to finish the problem. That's very easy. S is R theta. R was 9.3, and theta is 1.2537. Again, if a problem, it didn't say here, but if a problem says round your final answer to 2 decimal places, in intermediate calculations, you should go out much further. Don't round to 2 and then 2 at the end. Your answer will be way off. And if we punch this in, you get 9.3 times 1.2537. And I get, if I round to 2 places, 11.66. Now what are the units on this answer? Well, S is a length. It's an arc length, and so it's going to have the same units as the length of the radius, so that's inches. S is not an angle, right? S is a length, so it's going to have the same units as R. So that one's not too bad. We already know how to do conversions from degrees and minutes to decimal degrees. We already know how to go from decimal degrees to radians. That's nothing new, and plugging in the formula is easy. Like the key is you have to remember when you plug in for theta in a problem like this, theta has to be in radians. Now B is going the other way. Okay, so B is the same sort of problem here. Okay, I'm going to erase. Okay, it's still the same pulley with the 9.3 inches because this is part B. Through what angle to the nearest minute must the pulley be rotated to raise the weight 6 inches? So now they're saying the weight is going to come up 6 inches, so 6 inches of rope is going to get wrapped around, and now they want theta. And it says theta to the nearest minute. Okay. So let's do this problem again. Well, it's a different type. It's the same situation, but we're going in reverse. Well, they gave us S, and we know they gave us S and R. So S is R theta. S is the arc length, that's 6. R is the radius, which is 9.3. And theta is the angle that we don't know. Well, we can solve for theta here. That's easy, right? Theta, if you divide both sides by 9.3, theta is 6 over 9.3. Right? I'm not going to punch that in yet. Now what units is this angle in? Now the problem says through what angle to the nearest minute. So is this minutes? What is this? No. Remember I told you, if you plug in for theta, theta's in radians. If the formula spits out a theta, we solve for theta. The units are radians. This is radians. It doesn't matter what the problem says, right? So right now, theta's in radians. So what do we need to do? We need to convert this radians to the nearest minute. So what do we have to do? We have to go radians to decimal degrees and then to the nearest minute. All right, so I need to convert this. If you want to punch it in and decimal, you could, but I didn't bother because I know I was going to have to convert. Right, so I have 6 over 9.3 radians. I need to convert to decimal degrees. I need to get rid of the radians, so radians in the denominator, and degrees in the numerator. And then how many radians is how many degrees? Pi radians is 180 degrees. So if I punch all these numbers in, now be careful. If you want to type this whole thing in, 6 times 180 divided by 9.3 times pi, you need to put that entire numerator in parentheses. Again, don't put the units. And the entire denominator in parentheses. You have to do that or you're going to get the wrong answer. What I typically do is I do 6 times 180, enter, divided by 9.3, enter, divided by pi, enter. Then I don't have to worry about parentheses. I'm likely to make a mistake that way. Oops, I did it wrong. Look at that. 6 times 180 divided by 9.3 divided by pi. So this is about 36.96502 if I go all the way up it. Now that's degrees. Right, the radians cancel, and I included the pi in my computation. Now that's not what the problem asked for. The problem said to the nearest minute. So remember what you do. The answer here is going to be 36 degrees. Pull up the 36. And then what did we do with this decimal calculation to go to minutes? We multiplied that by 60. So remember when we went from degrees, minutes, seconds to decimal degrees, you divided by 60 and 3600. When you go from decimal degrees to minutes and seconds, you multiply by the 60. So 0.96502 times 60 is 57.9 minutes. 57.9. So this is 58 minutes. That's to the nearest minute. Now what if this problem had said, through what angle in radians must the pulley be rotated? Well, you'd be done, right? Just punch in 6 over 9.3 and write a decimal. That'd be your answer because that was radians, okay? So make sure you read the problem to see what type of units you want. If it said radians, you wouldn't have to do a conversion, okay? The only reason you have to do a conversion is because the formula spits out an angle in radians and it asks for to the nearest minute. That's the only reason we had to convert. If it said, what's the angle, in radians, punch that in, you're finished. Okay, so then the last idea, which is similar, it's the same picture, so draw the same picture again. I left space in the notes to do that. Okay. Get rid of the F's though. Okay, so now it's still a central angle in a circle of radius r, and the central angle I'm calling theta again. But this time we're interested in the area of the sector, which we're calling, using A for area. Okay? So it's the area of the pi piece there. That's called a sector, S-E-C-T-O-R. Okay, so it's the area of a sector. So I want a formula for the area in terms of theta and r, just like we found a formula for arc length in terms of theta and r. Well, I'm going to set this up the same way. So theta is in radians again. Theta is in radians. So when you plug theta into the formula, theta is in radians. If it spits out a theta, theta is in radians. Now you may say, well, why didn't we do this in degrees? We could have. The formula for S is r theta wouldn't have been as easy. We would have had some extra numbers in there, and same thing here. But notice, you'd still have the same problem. If we derive the formula for theta in degrees, if they gave us the angle in radians, we'd have to convert to degrees anyway. So it doesn't really matter. You might as well use the easier looking formula if you may have to convert one way or the other. Okay, now, I'm going to do the same thing I did before. It's reasonable that that angle divided by the angle all the way around would equal to the area of the sector divided by the area all the way around. Let me say that one more time. The fraction you get when you say this angle divided by the angle all the way around in radians would be the same fraction as that area of the sector divided by the area all the way around. Those two fractions would be the same. right? So the angle we have theta, divided by the angle all the way around. Again, we're in radians, so that's 2 pi, exactly the way it was with the arcing, is the area of this sector divided by the area all the way around. So what's the area of the entire circle? That's pi r squared. So you should know those formulas. You should know the area of a circle is pi times the radius squared. The circumference of a circle is 2 pi r. Okay, you should know those from geometry in high school. If you don't remember, I just told them to you, so make sure you know that. Well, we can cross multiply again. So 2 pi a is pi theta r squared. 2 pi a is pi theta r squared. Now notice they both have the pi's cancel. Okay, notice the 2 doesn't. The pi's cancel. So I have 2a is theta r squared. So how do we get a by itself? You can divide both sides by 2 or multiply by half. Same thing. I'm going to multiply by half. You get half theta r squared. So there's the formula for the area of a sector of a circle. It's 1/2 theta r squared. Okay, don't get the formulas confused. Arc length is S is r theta, where S is the arc length. The area of a sector is 1/2 theta r squared. Again, theta's in radians. Okay, let's do this last example here in the section. Okay, so it says, find the measure of a central angle, so we're looking for theta, of a sector of area 16 square inches. Remember, areas are measured in square units. Length is feet, length is yards, length is miles. Area is square inches, right? Because you have a length and a width. Square inches, square miles, etc. Right? So find the measure of a central angle, we're looking for theta, of a sector of area 16 square inches, so the area is 16 square inches, in a circle of radius 3. Okay, so let me just draw that rough sketch. Again, this isn't to scale, it's just so we can see. Find the measure of the central angle, I'll call it theta, and a sector of area 16 square inches, that's the area of the sector, in a circle of radius 3. Round your answer to the nearest second. Okay? So they want the answers in degrees, minutes, seconds. Well, the formula here, area, so the area, don't square the 16. The 16 is not being squared, the square is on the units. So 16, let me write the formula. Area is 1/2 theta r squared. So the area is 16, a half is a half. Theta we don't know. The radius is 3, so that's times 3 squared. So if I simplify the right-hand side, 3 squared is 9. 9 times a half is 9 halves. No problem, right? That's 9 times a half. That's 9 halves. Now, how do you solve for theta? You can divide both sides by 9 halves, or you can multiply both sides by 2 ninths, right? Right? If I multiply both sides by 2 ninths, notice the 2 ninths here and the 9 halves give you a 1, right? That's 1. So that's 32 ninths is theta. If you want to get punching and get decimal, you could. I was just trying to make it easy, so I wouldn't have to punch anything in. Now, what are the units on this 32 ninths? If you plug in for theta in the formula, theta must be in radians. If it spits out a theta, theta's in radians. So this is radians. Now, the problem said, give your answer to the nearest second. Okay, so what do we need to do with this theta? We need to convert to decimal degrees and then go to degrees, minutes, seconds. Okay, so theta here is 32 ninths. That's radians. Okay, so I want radians in the denominator, degrees in the numerator, and 180 degrees is pi radians. Again, when I punch all this in, I'm going to punch in the pi as well. So when I do that, it's 32 times 180. Again, you should punch along with me. Divided by 9, and then divided by the pi. And if you want to punch it all at once, it'd be 30 parentheses, 32 times 180 parentheses, divided by parentheses 9 times pi parentheses. I got 203.7183, that's degrees, right? The radians cancel, and you do that. Let me check it one more time. 32 203.783, right. Okay. So we want to go the nearest second. So again, you pull off the 203 degrees, and you multiply that decimal by 60, right? So 0.7183 times 60. Okay, so this is 43.098 minutes. That came from 60 times 0.7183. We did ones like this before. And now how do you go to seconds? you pull off the 43 minutes, and you do 60 times that decimal. So 60 times 0.098 is 5.88 seconds. That's almost 6. Okay, so that's the answer for that question. Again, if they had said give the answer in radians, we would have been done right here, because when you if you use the formula and it spits out theta, you solve for theta, that answer's in radians. So if the problem had said in radians, we would have been finished here. The only reason we converted is because it said find to the nearest second, and that's in radians. Okay, that's the last example in 4.1. That was a very long section.